Hello. Today we're going to be talking about how we take advantage of the memory hierarchy in order to get good performance. And we do that by using caching. So these are the topics we will talk about. And caching really is ubiquitous in modern computing. So it's all over the memory subsystem of the computer, but it's also in other places like your browser cache and in things like content delivery networks. So it's a really sort of fundamental computer science concept. So a cache is a small, fast memory that acts as a buffer or a staging area for a larger, slower memory. So for instance, this is the cache here that sits between the processor and some sort of slower memory. And so the data that is needed from the lower memory is transferred into the faster memory while the processor needs to access it. The data is often transferred in particular sizes called blocks or lines, cache lines. And the slower caches tend to use larger block sizes. We often talk about caches in terms of the hit or the miss rate. So a cache hit is when you look in the cache to try to find something and it's there. And then a cache miss is when you try to look for something and it's not there. And of course, if there's a miss, then you're going to have to go down to the next lowest level, the slower memory, in order to read a value in. So we want to kind of maximize our hit ratio and minimize our miss ratio. So we're thinking for a second about what kind of data structure we might like to use to implement caches. And the key here is that we need really fast lookups and containment checks. So if you've taken CS240, at this point you might want to pause the video and think about what data structure we could use that would give us this property. All right, so the thing we're going to use is something called a hash table. And this basically takes the real address of some place that we want to access in memory, and it does some sort of function on that address in order to look up the place in the cache where that address should be stored. And so one way of doing this very simply is to just do modular arithmetic and mod by the size of the cache. So in this case, memory is listed here at the bottom. And then this is the cache. So this is the smaller amount of memory that is going to serve as a buffer for this larger amount of memory. Here we have 8 slots. So the slot ID is just going to be the last 3 bits of the memory address because 2 to the 3 is 8. And so if we just mod by 8, each of these memory addresses, that's just like extracting the last 3 bits of the binary address, which means that every single address that ends with 001 is going to map to this gray slot here in the cache. And every single memory address that ends in 101 is going to map to this blue line in the cache. And of course, as you can clearly see, multiple addresses might map to the same cache slot. So this is called a conflict, and it's something that we'll have to deal with. But first, let's just make sure that we understand how this works. So suppose we have a 16-element cache now with slots labeled starting at 0. So what slot would we use to store a cached version of a data element that is stored at the address in hex of 4D6? And here are a couple of reminders and hints. So take a minute and see if you can figure out what the slot number would be for this memory address. Okay, so we have 16 slots, which means that we'll need 4 bits to number them all, because 2 to the 4th is 16. And because we'll need 4 bits, we can just look at the last hex digit of the address. And so modding by 4 is equivalent to extracting the last 4 bits, or the last hex digit. And so that's simply 6. So the slot number that this address needs to be stored at is slot 6. All right, so some more terminology. So a cache line or a block, again, is a sequence of bytes that is moved between memory levels in a single operation. A cache set is a collection of one or more cache lines. So our cache is going to be organized into these sets. Each cache line itself contains a tag to identify the source address, and a valid bit indicating whether the value is up to date. So this is our entire cache, which is composed of sets, which are composed of lines. So this is the general cache organization. It's worth studying this a little bit because it's fairly complicated, but we'll see more examples later on. So cache systems are parameterized using a couple of different quantities. So these are the terms that your textbook uses. So there's S, which is the number of sets. So that's the number of these groups of cache lines. There's E, which is the number of lines per set. So that's the number of cache lines in each one of these groupings. This is also referred to as the associativity of the cache. There's B, which is the block size, which is the number of bytes inside of each of these cache lines. And then there is little m, which is the number of bits for the memory address, which is the number of bits that we use in order to calculate the tag, the set index, and the block offset, which are various components here. So the total capacity of the cache are the total capacity of this smaller, faster memory is going to be the number of cache sets times the number of lines per set times the number of bytes per line. And then the number of tag bits is going to be computed based on some of these other quantities here. So it's going to be the total number of bits in our memory address minus the number of bits that we need for the set index, and then minus the number of bits we need for the block offset.